Today we're doing a demo on the AT-GDP rework station, and just a quick overview of the machine. Main unit, this piece would be the board holder. We have the optics for alignment of the component to the board, and on the right side we have two laptops. So the first laptop, that's the main control laptop with the software, which is displayed on the separate monitor. And then to the right of that is an optional side view camera, which is located over here for viewing the part as it's being reflowed. So it's more for process development observation, whereas the main camera, which is right over here, is for the actual alignment. So that's the machine. I'm gonna put the camera down and just go through the process and explain a few things as we go along. So the first step would be to take the circuit board and secure it in the board holder. And we have adjustable rails that move in and out depending on the size and the width of the board. On this particular unit, it's a large board holder. It's the AT-GDP-2 model. For boards as small as this, or even much larger, AT-GDP-1, which has a 14 by 12 board handling capability, would be optimal. This board holder is up to 16 by 20 inches, so it can handle much larger boards. But the process would be the same. We would take the board, secure it, and the tabs here move in and out. We want to make sure that as we're locking the board, we're not going to hit any of the adjacent small components around. So we'll look for the optimal spots and simply just tighten and push the rails in. So the rails can move in and out. We can move them at an angle depending on the board. But the idea is that we're locking the board in place. It's nice and firm, doesn't move around. So once we have the board in the locked position, the next step is to pick up a part that's being placed and optically align it. So we're gonna take the part out of the gel pack, and since it's a wafer level CSP, you want to be gentle with it in terms of taking it off. I'm just going to grab it along the opposite edges. And put it down. Doesn't matter in terms of where it's being placed. I'm going to place it next to the part. What does matter is the pin 1 orientation. So on this particular part, there's a solder ball that's missing, and it's easy to establish where pin 1 is. I'm just gonna try to zoom in. And once it's somewhere on the board, we're going to optically align the pickup tip, which is the brass tip that you see right inside of the reflow nozzle. And that is a tip that's used to pick and place parts. So in the software, we're going to click on the camera view icon and move the optics in position. So on the screen, we're looking at the board and the vacuum pad. So right here is the brass vacuum pad that is used to pick and place the part. By adjusting the light intensity, you can adjust green LEDs, which is the light that's directed at the vacuum pad. The white LEDs are directed at the circuit board. And here's that vacuum pad. So I'm going to get both images of the board and the vacuum pad and just look for that part. see if I just zoom out to get a rough orientation. And here's that part. So with the optics, we can adjust the zoom, the focus. That's the eye of the lens. And I'm just going to rotate this. What it does, it just magnifies the image on screen. So we're looking at an image of that part that's placed on the board, the vacuum pad that's going to be used to pick it up, as well as the placement location. So this part could have been placed anywhere. What really matters at this point is just making sure that the pin 1 orientation is correct. This way it will align over the parts or over the pads. One other thing is on this particular board, the pads were, the solder paste was placed on the pads and there was a bump on it. So the part cannot be placed on the particular board in that state because the solder balls of the CSP, once aligned, could be aligned perfectly, placed on the bumps of the pads. It would be a bump-to-bump contact and it would slide the part off. So the pads have to be flat. And this board had to be cleaned with basically a soldering station to level off the excess solder or the solder that was applied initially during the solder paste application process. But at this point, I'm just gonna place this down. So I can grab tweezers, kind of move this out. Just to get it roughly squared off. And at this point, the main thing that I'm looking for is getting the vacuum pad opening over the part. So if the pad is over, we're going to have vacuum suction. We're going to pick up the part. And that's what I'm going to do now. I'm going to move the optics, once it's aligned, roughly aligned, out of the way. And in the software, the menu icon here, I'm going to click on down to contact, and it's going to have the reflow head come down, make contact with that micro BGA or CSP, and then we're going to activate the vacuum and then move it back up. If the parts are presented in tape, there's a faster way of picking up the part using a positioning plate or even a feeder. But given that they were in the gel pack, it's essentially a manual process of taking the part out and placing it on the board. So I'm going to click on vacuum pad. That hissing sound is the vacuum in contact with the CSP. And then I'm going to click on to upper home. And slowly the head is going to move up along with that part with it. When the reflow head is closer to the board, the speed is decreased. It's software adjustable, but essentially to minimize the contact force, not to cause any damage to the part. Once it's away from the board, it moves a little faster. But in the home position, we're going to slide the optics back in place. And on the screen, we see that the part is now picked up, so we can see the solder balls. So that's the component held by the vacuum. These are the corresponding pads on the circuit board. And again, we can play around with the zoom, the focus, just to get the image clearly in view. Then there are also software adjustments in terms of digital zoom. Right now it's only optical zoom, but we can increase the digital zoom, the resolution as well. But in this state, it's large enough on a part that's roughly 1.5 millimeters squared. And the alignment process is essentially positioning the board holder, the PCB, over the spheres of that micro BGA. So to do that, we can slide the table. So this table, it's free floating on this granite base. There's an XY positioning stage. There's also a theta rotation adjustment. And simply sliding it, as I'm moving it with one hand, it's a little difficult to do this with one hand, and basically I'm just getting it roughly in position. It doesn't have to be perfect, because once I'm in an approximate placement position, I can use the micrometers just to show how that works. The micrometers to slide one image over the other. So we can play with the light intensity. So that's the part, that's the board. We can see essentially looking to get the two images, the images of the pads and the images of the spheres aligned. And once they're aligned, the component essentially is aligned as well. So we're almost ready to place the part down and start the soldering process. What we need to do at this point is to make sure that there's either solder paste, or more commonly used would be tacky or paste flux. Tacky paste flux is essentially, here's an example of one. There are many brands and options, but it's soldering flux, but it's more tacky than traditional soldering flux. It's more sticky. It's similar to the consistency of honey. The reason for that is it's able to withstand higher temperatures longer. So since the CSP already has solder on it, the solder balls are solder material, we don't necessarily need to have solder paste applied. Usually, the reason why solder paste was applied in this case was during the assembly process. A stencil is made. The stencil is going to have apertures for all of the solder paste, for all of the components, unless it's specifically masked off. And the process will be placing the parts and reflowing them. When we're working in this kind of an environment, rework or placing components post initial reflow on a BGA or a CSP or a micro BGA, it's not necessary. And using flux is a clean and a kind of efficient way to go about this. So one way to do this is applying the flux directly to the board, just using a small syringe. The other way, we have a plate called a flux dipping plate, and it's basically right there. That's a plate that's machined to a depth of half a ball diameter. We apply tacky flux, and using a spatula similar to this. This is one of them. You can use a smaller, wider. We wipe the flux flat and fill that little plate with a small amount of flux. And applying it, it's applied directly to the part. So instead of having an inconsistent volume applied to the component, we're just going to move the optics out of the way, swing the plate, and gently just lift up, make contact, and slide this over. So right now the component made contact with the flux, and there's an imprint. It can be hard to see on such a small component, but difficult to see here, but it makes a small imprint of flux, and it allows the oxidized layer of solder to be cleaned off during the soldering process and have the solder balls wet to the pads on the board. So if the flux is applied, at this point we're ready to do the alignment and placement and soldering. So the alignment is already done. We can just kind of move this over, double check, make sure that it hasn't moved in our process. So I'm just purposely sliding this left and right. It's all in place. So I'm gonna click on table lock. Table lock vacuum locks this table in place, so you don't accidentally bump it or shift it anyway. And we can move the optics out of position. On the screen, we're going to click on graph view, and that's our main graph. So we have a temperature in Celsius, time is in seconds, and I'm going to click on the profile tab. These are the settings for a profile. In this case, we can't really attach a thermocouple to the board and to the component because of its small size. So on an initial process, we're just going to estimate the settings, and there's some settings already predefined, so you can have a list of different profiles. Essentially just a recipe for a particular part on a board. And go back to the main screen. The mode is install. We're installing this component, and we can click start. So once start is initiated, this essentially is a hands-off process at this point. And turn the side camera on. That's just the light. And the head moves down. I'm just gonna place the component onto the board. So you can see it come down, make contact, and then vacuum shuts off and the head moves up. So we want the part to sit on the board without any pressure applied to the top. If there's pressure applied, it will cause the solder balls to splatter once the melting temperature is reached. So we just want it to be in this kind of a state as if the board is going through the original manufacturing process of pick and place and then reflow. So at this point, the heating process started. The way we typically program would be to have the infrared, the bottom side heaters, turn on and preheat the board. So we're warming the board up. The nozzle, I'm just going to move it down manually a little bit. The nozzle is covering the component. The way the temperatures are set, you don't have to really isolate the component around. We can have the nozzle slightly above it, and the temperatures are in the safe zone where they're not going to overheat or melt adjacent components. So at this point, the green line on the screen is that infrared preheater is just climbing up. The set value is, I believe it's 450 or 475 degrees, and again, everything is Celsius. It's important to know that the 475 is not the actual temperature of the board. It's the temperature of the sensor that's inside the infrared preheater. And usually the 475 only equates to about 150 to 200 C on the circuit board. So we're just warming the board up. The main purpose of the preheater is by warming the board up, we're reducing the peak temperature up top. So if we're just only applying the temperature at the top side, then we're going to have higher settings to achieve the melting state. And for that reason, we want to preheat the board. This way we're not setting the high temperatures up top, and ultimately there's this equilibrium of top and bottom. And here's the other side view of the component. Now in this case, we can't really profile in that we can't get a thermocouple in because the part is so small, and we're not sacrificing any one board. So what I'm looking for is to see the solder balls melt and have the part kind of collapse to the board, and we'll know that that's a state wherein the solder melts. We can save the settings in the software at that point, so we'll know this is a good reflow. If not, we can always go back and apply more heat. But without actually getting a thermocouple in there, and we have 5 thermocouple channels that can be plugged in, but in this particular instance, we're not sliding a thermocouple in because it's a part that's being installed. So we're gonna run based on the images we're seeing here. And in the software, the red line, that's the top side heater. That's the heater that's directing airflow at the top. So it's coming from the top here. So that's the main heater, that's the control heater. And one of the capabilities here is we can adjust the settings on the fly. So we can go back to the profile tab. If we see that the heater is set to 220C for 80 seconds, we can change the 80 seconds, we can change the temperature based on how the component looks on the screen. So far, the solder balls are still in the same state. Now it's gonna, again, at this point we're just preheating it, so it's not supposed to melt. We're just getting it to the temperature close to the melting point, and then it's going to spike up to the next temperature set point, which is, I believe, 275C. And the setting there is 80 seconds, so we'll get to 275. We're going to stay there for 80 seconds. If we see it melts before, then we can always go back and modify the time, reduce it, or if we feel like we need more time, we can do the same. We can increase that 80 seconds to 100 or 120 seconds and kind of make sure it reflows. Just gonna go back, change that to 120 seconds, give it some extra time. So at this point, it's almost complete. And in the install stage, what happens when the time at a peak temperature is complete, we have cooling, and the cooling is having essentially the heater turn off. In this state, heater turns off. And we have that hissing sound is the airflow. from the top coming down at the component level. And we also have fans up front and in the back of the preheater, and the fans cool the preheater and they cool the board as well. So it's cooling down. And on the graph we can see that as well. At this point the solder is solidified, so we're just cooling down to make sure the board is safe to pull out of the board holder. But that's basically it. So we have a couple of things. We have 3 heating sources. Heater is the main heater up top, and we have the local preheater, which is a small round boost preheater there that can be positioned directly under the board. Some profiles that have a lot of mass, we may choose to use both the infrared and the localized preheater. In some profiles we can run just the localized or just the infrared. So there's a lot of flexibility in terms of how they're processed. And then when the process is complete, the reflow head moves up and away. The fans are still running. So the process is technically still running. We will get a process is complete message. It's just how this was programmed. But the last heater, the air preheater TC, that's the infrared preheater that we have here, and that is the preheater that we were using in this case to get the board to about 150 to 200 C, warming it up, and then ultimately that allows us to have lower set point at the top to get to the same melting temperature. And then the profile tab, some of the settings here, we have a lag time of 100 seconds right here. That lag time just basically means that once we hit start, have the preheater turn on, wait 100 seconds, and then have the top heater kick in. And that's just some extra time for the board to kind of warm up a little bit. Then we have airflow, 1, 2, 3. That is the intensity of the airflow. So 1 is low, usually for components 5 millimeters and below. 2 would be from 5 millimeters up to 30, and then 3 is higher flow. It's from 30 millimeters squared and up. So having it at 1, even at 2, really would be low enough flow and gentle enough that it's not going to blow the part off. So it's going to keep the component in place. And some of the settings here for the top heater, that's the main heater, we have process complete. Let's acknowledge that. We have ramp, which is initial ramp of the red line. So it's 2 degrees Celsius per second to a set point of 220 Celsius in this case, and that's right there. And then we specify how long do we want to stay at that 220. In this case, it's 80 seconds. So it'd be this time on the graph right there. And then from this spot, once the 80 seconds are complete, then we'll go to the next ramp to the peak temperature. So the initial ramp to 220 for 80 seconds, it's just preheating. We're not melting it at this point, since the melting point of solder is 217 sec 305. This is 220. There's always going to be a delta between the air temperature and the actual solder joint temperature, and that delta could be 20 degrees, could be 30, could be 40. It just depends on the thermal mass of the board and the part. In this case, the part is insignificant mass, but the board does have some layers and it has some weight to it. So I would expect that there would be a delta between air and board of about 30 degrees Celsius. But anyway, from the 80 seconds, the next ramp is 2 degrees to a set point of 275 C for 120 seconds. That's the value that I changed from 80 to 120, but it would be this point. So it ramps at 2 degrees on the graph, reaches 275 and stays there for 120 seconds. So that's the main part of the profile. That's really, this section right here is the most common section of a profile that's being adjusted. It's the peak air temperature up top and the time that we stay at the temperature. This can go back and forth, but usually there's a pretty narrow window of about 60 to maybe 150 seconds is how we program that. And we set cooling to a certain temperature point. In this profile, we have area preheater, which is 5 degrees to 475 C for 600 seconds. And by default, the main heater is the top heater. So whether we set it to 500, 600, 1000, doesn't really matter. Once this is complete, it will automatically shut the area heater off. So again, 475 C on the area heater does not equate to 475 C on the board. It's close to 150 to 200 C on the circuit board. The air settings on the top heater are different. They actually correspond to the air temperature, so that for that reason they're much closer to the actual desired peak that we're trying to get, which is about 235 to maybe 255 C, so anywhere in that range, even though the melting point is 220 Celsius. And some other settings here, options. These are kind of global settings. This is the speed at which the reflow head moves up and down, so that's user defined. That can be adjusted. Usually they're all default, but calibration tab, that's factory settings basically for the top heater and the local heater. And that's basically it. So once the process is complete, we get a message process is complete. That's the component sitting on the circuit board. And that's the circuit board with the part installed. So at this point, it's just sitting in standby mode. We can leave the board in, we can take it out, take the next board in, but that is the overall process.